Okay, let's continue what we learned last week, which is the finite state machine. So last week we have learned a lot actually. You have been introduced to the more type state machine where we have looked at this example, yeah, the automatic speed regulated vehicle where we have derived the state diagram like this, right? And we have derived the circuit, yeah. And we also have learned how to derive or how to write the Verilog program, Verilog code to represent this, yeah. So uh, in conclusion, with Verilog, if you have the state diagram like this, so you don't need to derive the circuit like this because we can describe the state machine using behavioral modeling like this. This is the behavior where, for example, if we are in state A, so if W, the input, is equal to 1, so the next state will be equal to B, right? But if W equal to 0, the next state should be equal to A, right? So this directly reflect this state diagram, right? And we have learned also last week that if our state machine is the more type state machine, we don't have this wire, right? But if our state machine is the mealy type, yeah, the second type of finite state machine, which is the mealy type state machine. So we have this wire. This wire, with this wire means that the output here, Z, is not only depend on this only, but it is depend on the input also. All right. But for more, if we don't have this, means that the output Z is only depend on the output of the flip-flops, or in other words, we call it the state of the flip-flops. Now let's see uh, how we derive the mealy state machine. All right. So this is mealy, MEALY state machine or mealy state model. uh, I forgot to have this line here, right? So in your notes, please draw this line from this to this for the mealy state machine. And the difference is that if we have this line, if we compare with the output with the previous one, the more here, right? Let's compare. So compare. Let's snap this. Okay, so this is the milli. Yeah, this is the more from the more state machine. So we can see that if we have the sequence like this is the uh, measurement interval. All right. So at T1, so the speed is exceeding the speed limit, but after that there is no the speed is going down, so the output is 0. And remember, for more, the output is delay for one cycle. Delay for one cycle. So here we have two consecutive speed exceeding the speed limit. So we have one here, and here we have one. We have one here, and here one still one. So the output is 1. But for milli, when we look at milli, we can see that 1, yes, still 1, but the output here is not delayed by one cycle. It is immediately appear here at the Z. For example, here 1 1, so the output is 1 here, right? Here 1 1, the output immediately appear here 1 1 1, we have 1, because of the wire here, means that Z will immediately change when W change, right? Because of this wire. If we don't have, means that Z will depend on the state of the flip-flop. That's why it's delay one cycle. Okay, so this is the state diagram of the milli-state machine for the same application, for the same problem here, right? The automatic speed regulated vehicle. So let's see how to draw this, how to get this state diagram. So I will use this. Okay. So now for the state, let's say this is state A or state 1 or state 0. Uh, so you can use any name for the state. And when you reset, you will always we have reset here. When we reset, so we will always be in state A, the first state. And for milli, this is again same as the more type. The input W is W equal to 1, so we remain at A. But the difference between the milli and more is that the output. So for more, the output Z is in the state, right? Z equal to 0. Remember last time? When we look at the more, the output Z is in the state. But for the milli, the output is at the state transition. So if W equal to 1 here, so here Z should be equal to 0. So the output at the transition, not in the state. That is the characteristic of the milli state machine. And of course, if W equal to 0, sorry, this is if the W equal to 0. If W equal to 0, so Z should be equal to 0, and we remain at state A. But if Z equal to 1, so we cannot remain at A, all right? If not, we will be at A forever. So if W equal to 1, so we should go to other state, for example, state B, right? And again, the output is within the state transition. So here is only one W here, and W equal to 1 only one time. So Z should be equal to 0. Yeah, still equal to 0 here. And we go to state B. And at B, if Z equal to 1, sorry, if w equal to 1, so here z can be equal to 1 here, because if w equal to 1 here, yes, z equal to 0, but if, sorry, if w equal to 1 here, z equal to 0, and the next, if w equal to 1, now z equal to 1 and stay here. And again, if w still equal to 1, so z should remain 1. So it should be something like this. This is w, this is z. So if 0, 0, yes, we remain at A, But if 1, we go to B, but here z should be equal to 0. Now if 1 come here, we should remain at B, and z should be equal to 1 here. And if still w equal to 1, so we should remain at B, and z should remain 1. Means that it is exceeding the speed, and we need to reduce the speed until we have w equal to 0, then z should be equal to 0. But of course, if this happen, we cannot stay at B. We need to go somewhere else. In this case, we can go back. All right? Because if w equal to 0, z should be equal to 0. And if it is remain 0, if w remains 0 here, yeah, we remain at A, and z should be remain 0. If another w equal to 1, this should be A. And if w equal to 1, the next one, z should be still 0. And we now at B. And if z equal to 0, w equal to 0, then we go back to A, and z should be equal to 0, which is okay. Next, if 1 again, we go to B, and still 0. But if another 1 come, means that we remain at B, and z now equal to 1, and so on. Right? So that is how we derive the Mealy state diagram. Okay, so this is the Mealy state diagram. And again, the process to derive the logic circuit is that we need to generate the state table and also the state assigned table. So the state table here, because we have A and B only, so we have present state A and B. The next state is when w equal to 0 and w equal to 1. So if we are in A, if w equal to 0, so we remain at A, right? But if w equal to 1, we go to B. And what about output? So output, we have two conditions now, because if w equal to 0, z equal to 0. But if w equal to 1, z equal to 0 also. Right? But this path. For B, when we are in state B, the next state, when w equal to 0, we need to go to A. But when w equal to 1, we remain at B. Right? For Z, when w equal to 0, z equal to 0. When w equal to 1, z equal to 1. So we have state table. And remember, state table is represent this transition and the transition here, but we cannot derive the logic equation from this yet, because this is AB, the alphabet, not represented by the memory, by the binary number yet. And remember, to design the logic circuit, we need to represent everything in binary. So in this case, we only have two states. All right. So if we have two states, we can represent, we can use one one bit only, right? Because one bit we can represent 0, or can have two states, 0 and 1. All right, so we can represent 0 as A, 1 as B. Okay, now we change here A to 0, B to 1. So we have 0, 0, we have 1, 1. Z should be remain the same. Now we have this. From this, we can generate the uh, logic equation, and from logic equation, we can get the circuit. So this one is very easy. Z to get this Y. So Y should be equal to W, right? So that's why Y equal to W here. Here. Remember how to generate this. How to generate the circuit from this state assigned table. We need to go back to this, where the general structure of the finite state machine is always like this. We have the flip-flops, and we have the output logic, and we have the next state logic. This is called next state logic. This is called an output logic. All right, and for melee, we have this, and of course we have the output. In our case is Z, and always, we have this is the feedback, and now this one is 1 bit, 1 bit. Why 1 bit? Because we have only one this, Y, small y, capital Y, all are 1 bit. Why 1 bit? Because we only have two states. All right, two state, use 1 bit to represent these two states is enough. All right, one number 0, one number 1. If we have more than two states, you cannot use 1 bit, because 1 bit can only represent up to two numbers, two possible numbers. If you have 3 or 4, you need to have 2 bit, because 2 bit you can represent up to four states, and 1 bit means 1 flip-flops. All right, 2 bit means 2 flip-flops, 3 bit means 3 flip-flop. So in this case, we have only 1 flip-flop, and this is small y, or we call it present state signal. This is capital Y, or we call it next state signal. And we have one input, which is W. Okay, and remember, because this is maybe I have this. This is melee, so we also have this as the input to this for melee. All right. So now we need to determine what is the logic circuit here. The logic circuit inside this box, and also this one. So if you look carefully, here first, next state. So for next state, we have the output is capital Y, the input is W and small y, right? W and small y. So from the this state assigned table, it is just like the truth table, right? So with this, if we change this to or simplify this to a simple truth table, so we can have something like this. Or a K-map, right? This is like the K-map already, because you have Y, you have W here. If Y equal to 0, if Y equal to 1, if W equal to 0, if W equal to 1, right? Exactly this, W equal to 0, W equal to 1, Y equal to 0, Y equal to 1. So Y, so you have 0, 0, 1, 1. So this is 0, 0, 1, 1 in your map. So you have Y should be equal to, what is this? W, right? That's why you have Y equal to W. And what about Z? Z is easy. Here, W equal to 1. Z is 1 when W equal to 1, and here. W equal to 1 and small y equal to 1. So Z should be Y, W or W, Y. And when we draw, so Z should be this. Yeah. It's turned out that where to put here? Here. It's turned out that this inside the box is only one AND gate. So where the input of this AND gate is, okay, this Y and this W. This W, you see, W and Y. So you have that. So this is AND gate actually. And what about this? This one, because we have Y equal to W, so actually a wire only. Or actually it is a wire, right? Because capital Y here is equal to W, so there is no logic gate. So you just connect directly to this, and you get the answer. Okay, so now this is the Verilog code or Verilog program to represent that. This is quite straightforward actually. And the good thing about Verilog is, again, you don't need to do this actually. You don't need to have state table. You don't need to have the state assigned table. You don't need to have the logic circuit or equation. If you have the state diagram, you can straight away derive your Verilog code. So in this case, and of course you need to have this, you need to have this. This is important. So let's go to this. the Verilog code of this. Okay, can you see that? Bigger. Okay, and we need this. All right, this is important, because in order to derive this, we need the structure of our state machine. So this is the structure of the state machine without knowing what is inside this box and this box. We just refer to this. Okay, now let's derive this. So we have module name. For example, we name it milli. We have clock. So this is the clock. The reset. Of course, we need a reset signal. Okay, the reset, the W. Yeah. And the output Z. Okay, we have that. Should be enough. Clock. Look at this. The input, only the clock, the reset, the W, and the Z. These all are internal wire. And input, clock, reset, W, and the output Z. And again, because Z, we will describe using behavioral modeling. So we need to define Z as rect as well, right? That's why we have output rect Z. And we have these two will be described using behavioral modeling also. So we need to define this as rect, yeah, small y and y, and parameter to represent the state. So A is equal to 0, 1 bit, and B is 1. A is equal to 0, B is equal to 1. And we have this. This is to define the logic block here and also here. So we can use always input. So we have two input. That's why we have W here, W, and we have Y here. Right? Input to this, we have W and Y. Input to this also W and Y. So case Y, because Y is the state, yeah, present state, right? Y. If Y equal to A, means that if the state is equal to 0, yeah, A, because A is equal to 0, or state A, so we can use A here because we represent A with 0 with A here in parameter, so we can use A here. So if W equal to 1, all right, if W equal to 1, so if we are in state A, if W equal to 1, Z should be equal to 0. Z should be equal to 0. And the next state, which is, what is next state? Next state is capital Y, see? The next state, Y, capital Y. The next state should be B. Capital Y should be B. And finish, yeah? Done. If we are at A, if W equal to 1, so we should go here. But if W equal to 0, so we should remain at A. So this is if W equal to 0, or in this case, we use else. So Z should be equal to 0, yeah? And the next state should be equal to A, right? This is exactly the same as this. And done for A. And for B, if we are in B, if W equal to 1, so Z should be equal to 1. So Z should be equal to 1, and the next state should be equal to B, right? That's why we put B here. And if the else should be here, and if W equal to 0, so Z should be equal to 0, and the next state should be equal to A. The next state should be equal to A. Done. Right? And done for these two. We can generate Z and Y already. Now we need to describe these flip-flops. So to describe this flip-flop is easy, straightforward. So this one is negative H. In this case, it's negative H. Oh, sorry. The negative is the reset. So the reset is this negative H reset, positive flop. If reset equal to 0, so Y is equal to A. Right? If the reset equal to 0, Y equal to A. What is meant by Y equal to A means that the output here, small y here, equal to 0, right? Because A is 0. Means that when reset, we are at state A. But if not reset, or if reset equal to 1, so small y here should be equal to capital Y. That's why we have this. Small y should be equal to capital Y. Then we get these flip-flops. Then end module. So you see, the Verilog code is quite straightforward. Not that difficult if we have this. And this is standard structure, right? The difference between the other problem is that the input and the output later on we will see, because this one we have only one input and one output. But next time, yeah, for other example, we may have more than one input and more than one output. But the structure, the main structure is still the same like this. And the difference is the number of input and the number of output, right? And if we have this, and also we have the state diagram here, we can easily describe or derive the Verilog code for this. Okay, so from that, we also now can write the Verilog code. So I have here the Verilog code. I just share with you. I need to invoke the quarters. Okay, so this is quarters. So I have the program already. Yeah. So this is the code, exactly the same code, except that I have the state register before the next state and output logic. So this is the milli type, exactly the same with or describe this thing, this. Okay, and I have the test bench already. So this is the test bench, right? And this is actually the same test bench with the previous example, the more state machine. And let's run the code. Okay, so this is the output. Hope you can see this. And we can see that this is W, right? And this is state, yeah? This is state and this is Z. So if for this W equal to 1 this time, so we can see that Z will remain 0 because the next cycle W is 0 already. So there is no different. There is no different for Z. And here W go to 1 again, and because the next cycle W is going down back to 0, so Z will remain 0. And this is the state changing from here, because this is state 0 and go to state 1 here. Right, because Z equal to 1 here, so it go to the state 1 for the next cycle, right, and go back to state 0. And let's see here, when W equal to 1 here, and the next measurement W still equal to 1, now Z go to 1 immediately, right, immediately at state 1 or state B in our case, right? And the next measurement W still 0 equal to 1, so Z should remain 1, and we are still in state B, right? And now go to 0, and Z is 0, and we go back to state A in the next clock cycle, right? So when we look at the output here, when we compare with the output for the more, so let's compare with the more one. But before that, let's copy this so that we can compare with the more. Okay, so I open the one that we have last week, the more type. Should be this one. Yes, this is the more state diagram, and just simulate this. Okay, so this is the state. Here we compare with this one. So this is the more. We can see for the more, the output here, yeah, we have the exactly the same input. Yeah, the W equal to 1 here, W equal to 1 here, W equal to 1 here, 1 here, and another one is here. But see, for the more type, this one is milli. For the more type, the output here is delay 1 cycle here, right? Because we have 1 1, and Z equal to 1 after 1 cycle, after 1 clock cycle here. But here we can see that 1 1 here is immediately 1 here. Yeah, the W equal to 1 here. Not the W, this should be Z, right? So this is Z equal to 1 here immediately. But for more, we have 1 cycle delay here. Okay. The reason why is that we have line, this line, yeah, this. The reason is that Z for milli is depend directly with to W, the input here, right? So that is why Z will change immediately when W change, right? So that will be the milli type finite state machine. Okay, so we are at almost 4. So we will have a 5-minute break and come back at 4 5 minutes.